as you know, we have a great opportunity to have an address by the Director of the National Weather Service. And Louis used to do this exact kind of thing with much uglier and scarier equipment in prior years. But he's going to show us some of the historical stuff that he has from prior discussions. And you said last night in your talk, Lou, that you guys used to concoct research papers and whatnot at this thing. That is still true. I can tell you that. Yeah. We've had several things come out of discussions in this forum that have turned into research papers. This is an off-the-books dynamic seminar. That's what it's been. I mean, effectively for 20 years. And so it's been really excellent. So we're thrilled to have you here and tell us about some of the old stuff.
You should be able to see with the lights on, yes? I hope. Yeah.
Yeah.
So turn the lights on for a minute. So, first of all, I'm not running out of things to say. So last night, Lindsay gave me a ride to the, right? And the new word I learned was darty. The new word, the expression darty day party. Who told me to
do Rebecca told you.
Rebecca.
That's not me.
So I just sent an email back. We ran into Bucky Badger, got a picture of Donna and Bucky together. And I actually used the new word I learned yesterday in the email I sent back to the troops. But she's been converted. She's really feels a real strong pull to Wisconsin. I don't know if she'll go to graduate school. If she does, this will be high on the list. So anyway, the darty has begun across the street. Okay, so what I said to John was, the weekly weather watch back in the day, as far as I remember, it was organized by Dave Barber, who was my first TA, and Lyle Horn. And the idea was for student volunteers. You had to sign up to do it. So Lyle never gave a weekly weather watch. It was always the students. And it was open to undergraduate students, but it was mostly graduate students. And for many of us, it was the first time we got to talk about something in front of an audience. Hopefully a friendly audience. But you also had to make the forecast, and that's when it got unfriendly. Because everybody had their own opinion about what would happen, right? But one of the things, and I said this last night, that like all of the gravity wave work I did started in the fax room. The jet stream coupling work started in the fax room as we were preparing on. And the lateral coupling actually started in the fax room in preparation for this. Now, there you go. Silence your phone. I need a public service announcement. So this was the big step up, by the way. We used to have a machine, I forget what it was called.
It's an opaque projector.
Opaque projector. You had to actually crank you developed a scroll when you did the weekly weather watch. And you started with Sunday and you went right through the week, and then it was your projected forecast. And you sat here and you cranked the thing through, and that was a pain. What they had here was they had a base map, and then you could tap your slides together. So I don't have that base map thing, but this is the original. Like I said last night, I drive my wife nuts because I kept everything. I got boxes and stuff. So I went rummaging through, and the part I did the weekly weather watch with the idea that we were going to do it in isentropic coordinates, not in pressure coordinates, because this school actually at the time was promoting the use of isentropic representation and getting away from P surfaces. So when I did the modeling, I did a hybrid model, isentropic over sigma. So you can actually construct, you take an isotherm on 850, you find the areas where the cross isotherm flow, and everybody's interested in warm air advection, right, as a sort of an indication of vertical motion. And this isotherm happened to correspond with the 291 surface, so then you go up to sounding and you find out what isotherm at 700 corresponds with 291, and then 500. And so this is how you get this isentropic map. And what I was seeing was that the upslope flow on an isentropic surface from higher pressure to lower pressure, and the inference of vertical motion from there was happening right in between these two jets. Indirect circulation, Gaussian band should be here. Direct circulation of this entrance region, the rising motion should be there. So that's where, and then this is where the precip was happening. So that was one case. That map wound up being a figure in the very first paper published in the National Weather Digest, the National Weather Association. And it wasn't just the only case. That was in 75 and 76. I started doing this. And in this case, this week, particular week, there were 2 cases that this was very clear. Happening here. And this vertical motion went right up through 700 millibars, right into here. And then that was the 15th of February. And then the new case that was coming in, this, that was 15th Sunday morning. And then that system was moving on out. And then you had the next case come in. And there you start having your, the flow turning to the right, coming up here, and then on into that. So I started seeing this and published this in the National Weather Digest. And then as we started looking at the East Coast storms, as I showed last night, a lot of the cases, I can't say all of them, but a lot of the cases had this double jet structure for the East Coast storms. And why it was particularly important along the East Coast is that not just what's going on with the rising motion in the indirect circulation, but the direct circulation was actually forcing the cold air, locking the cold air right along the coast, so you didn't get to change over to rain. It stayed all snow. And that's become the lateral coupling paper that I wrote in Weather and Forecasting with Paul, and then we incorporated that in the book. That all started here. So that's basically what I wanted to emphasize. And I got to tell you, my last, I think it was the 76. I'm sure it was 76. It might have been, yeah, it was in February of 76. So that was this one here. My parents were in the audience, and my aunt was in the audience, my mother's sister. And so I went through the whole thing, made the forecast, and there was a big potential for snow. So I went for an 8-inch snowfall, which was where we got the call. That night, I asked my mother if she liked what she heard. She said, I didn't understand a word, but I loved it, right? So I was telling this guy, I said, great, great. I said, so my father said, man, he said, I didn't see any acceptance of the forecast. So we had a situation where I lived at that point 4 miles west of town. We had 4 to 5 inches of snow, and then when I woke up, and I thought, great. And I verified it was raining here. It was a rain mixed with snow. So I started getting calls at 9, 10 in the morning about how it blew the forecast. I had, members of the softball team were kind, sort of preparing me for the future. Hey, you blew the forecast, your parents are in the audience, That afternoon, the second area precip came over and dumped 8 inches of snow here. So I was making phone calls back that evening, right? So anyway, it was, this was a real, like John, you alluded to it, this was a real, and Lyle would sit right there, have his lunch while this was going on. There were always arguments. It was a lot more of a contact sport. And he'd just sit there, smile, eating his lunch. And I would say that Lyle Horn was really the soul. I've said this over and over, and I'll emphasize it here. He was the soul of the department because he really took care of students. It didn't make any difference whether you were his student or not. He was just, he was for the whole department. So that's basically what I wanted to share.
Right. A couple questions, or 3 questions. One, the 4 panel maps that you're showing there, were your base maps based on like the LFM maps? I see how you have those 4 panels there. Are they, do you trace as your base map those fax maps? To superimpose on
that? No, because what I did was, the idea was try to compress.
Right.
There were students that gave their briefings would only show single panel, and then you'd have a stack of maps like this. So, one of the things here was just to compress it. But we did things like, I always wanted to I like the 500 millibar heights, but from a jet streak perspective, I wanted to show the 300 millibar winds. In here, I did not want to do the 850 millibar map, because that, by the way, I always felt like pressure coordinates were the reason why people looked at 850 separate from what was going on aloft, right? So one of the things I was trying to show, remember I was also doing the vertical coupling here, that this isn't, you know, horizontal flow. This is a slope flow, right? And if you look at the omega equation in isotopic coordinates, you know, the dp, dt, you have that advective term, and you have in here, so it really becomes a matter of how fast this is moving. There are cases where this compresses down and actually shifts to the south, even as this is rising up, you know, at that point. And that's what happens as the East Coast storms spin up, by the way. And you get this gradient not moving with this wind, and that would be zero vertical motion in that equation, but actually shifting down. And that's an interesting part. It has to do with the vertical cooling going on and all that. So it's the idea here was to get the slope response and start, you know, really emphasizing how you can get this.
So follow up on that. So your use of isotropic analysis in your past work, and now being at an organization that produces a lot of really great products on the MAG site, particularly the output from the forecast models. Any thought to perhaps having some of those products on the MAG site be isotropic?
Well, one of the things we've done internally is that within GEMPAC you can actually create your isotopic maps.
Right, but just having them already pre-made.
Pre-made. Yeah, so I've sold out in a sense. It was hard to, first of all, when we developed the MAG site, we were actually had more limitations in space. And one of the things we were going for was to get more people looking at it. So that's why we've got in fact, Pete, what I saw here in terms of the post-processing of our models, and then what I started seeing from the University of Michigan is what motivated us just to get something out there. I've talked to Lance about this, and he's not, he's like, he's saying, you know, you're really up against the trend of what people will actually look at, right? So it might be an interesting experiment, because we can actually track what people are looking at.
And then the final question is, one actually nailed the MAG site earlier this week. It's something that's just annoyed me about these maps. Why do you,
when something annoys you, write me an email.
Okay. Why is geostrophic, absolute geostrophic vorticity plotted on the MAG site as opposed to just vorticity? Given that you have the winds, it may be a little bit messier, but why geostrophic vorticity?
You know, I can't answer that question. I don't know. I don't know why that was selected. You know, Ralph Peterson was actually involved in the original selection of. What I have found is that people aren't even looking at the vorticity advection anymore. They're going right to the vertical motion fields, and that's what I try to encourage. Is why the hell are we even dealing with warm air advection and geostrophic advection when you got the vertical motion field? And I remind, and I'll get on my soapbox now. You know. There's a sentence in Holton that people tend to ignore, you know, that the effective fields that we relate to vertical motion is to get the flow field back into balance or to sustain balance. And in situations like this, and like I showed the gravity wave stuff yesterday, that's not what's happening, folks. The atmosphere is going out of balance. And that's what the vertical motion field may or may not be acting to restore that balance, okay? So it's, I think it's led us down a wrong path. You know, it's been good. The effective fields were a good thing to have when you couldn't diagnose vertical motion, and nobody trusted the vertical motion in the initial numerical models because it's very noisy and all that. But now, if you go to the vertical motion field, it's not balance constrained. If you try to relate, and don't show me a Q vector. Why? Because that's the field that's bringing you back into balance.
So you're talking about a primary flow moving up sloping isotropes as your vertical motion driver.
But I am not assuming. I'm saying that this. I'm very careful here in terms of a representation of the field. But you've actually got to actually compute the vertical motion from this. You got to have the time tendencies and everything else. What I'm saying is that in the model fields today, you're getting the vertical motion generated not only by the primitive equations, but by the diabatic fields that are interacting with that dynamical process. And Q vectors are not a representation of that process.
But you can't attribute that output to any set of physical processes. You can't separate.
What's wrong with the primitive equation?
They don't tell you anything except the answer. Tell me how they tell you. How do they tell you about what's forcing the vertical motion?
What they're doing is they're allowing these fields to evolve in such a way that vertical motion can be forced, right? By mechanical processes where you don't have to make assumptions. You don't have to make assumptions to infer. This is the point I'm trying to make with the prosecutor. You're inferring vertical motion based on an assumption that these effective fields that you're using to infer is driving you back towards a geostrophic and a hydrostatic balance. So why the hell are we then spending all this money on numerical models that are non-hydrostatic, generating a vertical motion field, and people will start, the first thing they want to do is apply a Q vector to it. I don't get it. And in fact, when I've seen examples of the Q vector, you look at those fields and you say, vertical motion isn't there, it's over here. Okay, well, what's doing that? I never get an answer from the
products.
Well, I want to agree with you on that. I totally agree that when you look at the primitive equation, you look at the explicit vertical motion, there's so much in there to see. You learn every time you look at it, and it's an education process to see what's actually driving these things. And in many cases, it's the physical balance is exploding, and that's the process you're interested in.
Yeah, but how do you separate it from the part that's not unbalanced? How do you do that?
That's
what I'm.
Well, I don't think they're not separated. They're not separated.
You should. That gives you
they're
more
all
insight
one
about the way
thing.
nature works. I think my philosophy is probably not 100% right, but I think that what that gives you is the answer. It doesn't give you insight. There's a difference.
I think it gives you false insight.
gives you the wrong answer.
It gives you the wrong answer,
there's a wrong
and you believe what's
I can tell
happening
you
for the
why
wrong reason.
upper fronts form
That's
without
exactly
lights
right.
on,
That's
and lights
exactly
on.
right.
It's over at Grant. You want to turn that? That's the far left one. There you go.
So, as I showed in the paper, on the first paper on the President's Storm, and it's like, did anybody have chalk anymore? Here we go.
No, we just have the primitive equations.
You should use them. Okay, so there's a ridge. There's a ridge crest. In the President's Day Storm paper, the first paper we wrote and the third paper. First was based on data, second was on the models. We had an amplifying subtropical jet coming towards a ridge crest. Now, Kaplan and Payne showed, and as the jet was amplifying, it was like at 80 meters per second. All right? So, as Kaplan and Payne showed, with the divergence equations, when you have a U momentum surge approaching a negative Laplacian, both terms of the divergence equation are the same sign. So a U momentum surge is a jet stream, and a negative Laplacian is a ridge. And they were emphasizing that a jet approaching a ridge, you're going towards unbalanced flow. Okay? In the President's Day Storm, this is your height field, simplified. The geostrophic max was actually back here. And the 80 meter per second, actually, was up here. You were in the exit region of the geostrophic wind max, and you were in the entrance region of the total wind max. If you do a Q vector, right, you're going to get your wind field, your geostrophic wind field like that. From a real wind perspective, we were getting this. And in fact, the flow through the ridge crest was doing this and this. It was actually accelerating through the ridge crest. You had cross flow accelerating through the ridge crest. It was totally unbalanced. Your Q vector was not only not giving you insight, it was giving you the wrong sign.
No, I disagree. I think if you compare your primitive equation omega to your QG omega,
I'm telling you, the agostrophic wind coming out of this, UG dot del UG, the gradient, was giving you the wrong sign.
I know, but that sets you up to see that explicitly, having both.
Nobody could explain it until I actually did trajectories. Nobody in the discussion would buy that this was happening until we did the trajectory flow, which is another thing that this field has gotten away from, is actually computing. It's hard. It's not easy. But you've got to take the Lagrangian view to help you understand how this is interacting. So let's have a discussion on that paper. Go through the paper and let's have a discussion.
Okay.
All right.
One thing I found.
And show me the Q vectors that's providing the insight that's not the wrong. I'm not only getting the wrong, I'm getting the wrong sign. How is that giving me insight?
One thing that happens is as you affect angular momentum forward toward this jet stream, you increase the negative, or you decrease the relative vorticity. It gets smaller and smaller, and it reaches a threshold where it gets so small that the Rossby radius of deformation gets so big that balance flow just disappears. It just goes away right at the important time in the system. And when the balance flow goes away, the system breaks up into other things like gravity waves, and it's really interesting to watch.
So, by the way, I agree with that. This is what Kaplan and Payne were actually pointing towards, was the creation of how a large-scale flow field would provide the environment for small-scale waves that would have to. They got blown out of the water. People said they were crazy. Right? Now they had a way of presenting it which was more combative than my interaction with John here. So, Lance Bozarth wrote his original paper with this flow into the ridge, because it was going through ridge, as evidence that there was no upper level forcing for the initial development phase of the President's Day cyclone. That's what got me involved in this study in the first place. We got 7 to 14 inches of snow under a ridge.
Yeah, I mean, there's a tremendous supergeostrophic flow there. And there's going to be divergence and convergence coupled surrounding it. I can't imagine why anyone
It
would
wasn't
have
only
to do that.
supergeostrophic, it was accelerating through the ridge. And number one, and number two, I'm trying to tell you, this is what you get from the quasi-geostrophic approach, which was the wrong sign. And it was displacing everything back here closer to the trough.
I'm not arguing with that. I'm just saying that if you have both at hand, you can see exactly how wrong it is.
You can only
And
get
that's
the insight on this if you go to the primitive equations.
I don't think we just-
Q vector gives you the wrong sign, doesn't do anything. Doesn't do anything for me. I will use it. Now, K vector, you're getting close.
No, I'm going to send you a paper on upper fronts that uses QG omega. You'll like it a lot.
Do you do it with a jet flow approaching the ridge crest?
It's
Probably
approaching
not. This is, by the way, you're taught in synoptics that the ridge is the ugly duckling of meteorology. Nothing interesting happens. This is where you get your most dynamically interesting things going on, number one. So when Maddox was telling me there was no upper level forcing for MCSs, and then he comes up with a schematic that looks like this, with a weak jet, but still long stream variation, and the MCSs are occurring right here. And I'm saying, wait a minute, go back and read Kaplan and Payne. This is where you would expect the dynamic. It doesn't have to be that large in the middle of August and July. You're sitting with a boundary layer that's ready to pop. So cyclogenesis, the cyclic self-development. You're doing a thing on cyclic, right?
Yeah.
Yeah. Same thing. These wavelengths have to get smaller, right? The jet doesn't come around the trough. It regenerates on the eastern side of the trough, approaching the ridge crest. Dynamically unstable. Cyclogenesis. That's where it's at. And I didn't get the insight by doing quasi-geostrophic. I got it by actually computing trajectories using the primitive equation. I went to semi-geostrophic, so I allowed myself the total wind. Semi-geostrophic gets you the right sign, rowing magnitude. Quasi-geostrophic gives you the wrong sign, right? Right sign, but low magnitude, and then using the total primitive equations, you can actually diagnose what's going on here and get the right vertical motion in the right place. That was my experience with it.
Well, I think it's a question of what is the question you're trying to answer?
And I don't think the quasi-geostrophic approach that uses effective fields as a basis for trying to understand the evolution in a pre-storm, during storm, and after-storm environment is giving you the right answers. I think what it's giving you is, based on the assumptions of always forcing it towards a balanced state, is actually misleading. Number one. Number two is, the other rat hole that Levis found was that what's happening at 850 is not necessarily connected to 500. And one of the important things I did in that paper, the review paper that I wrote in 1990, is I rediscovered Sutcliffe. In the 1930s, Sutcliffe actually tried to connect what was happening in the low levels to the upper levels through the evolution of a cyclone. That's what I thought made his work brilliant, and certainly ahead of his time.
Way
So, so way ahead. So the last section in the paper is to go back to the Sutcliffe self-development concept. Right? But that's not what was happening in the 70s and 80s. People kept on looking at low-level forcing related to warm air advection and upper-level forcing related to PVA, right? And if you didn't have PVA there, that they, wherever they were diagnosing it from, oh, this is a low-level forced environment, and it's a different kind of cyclone. That's what they were promoting. It was a new kind of cyclogenesis forced in the low levels, okay? You read Rover's papers and that tail that goes out there, you read Jackham's work for the QE2, that was the rat hole that was leading us down. And it was all on this separation of those two terms from a quasi-geostrophic perspective that started that path.
But
That's
the
a
Q-vector
bad
approach,
separation. Yeah, go
right.
ahead, Michael.
The Q-vector approach, though, gets rid of talking about these separate levels, right? Because it only, you can diagnose, in a crude sense, the vertical motion by looking at it on one level, or if you look at a volume constructed Q-vector divergence or convergence field.
Yeah.
So it doesn't, so the separation issue, I think, is a false one, because
Well, no, that was the second one. The Q-vector was that if you apply it here and you relay it strictly to quasi-geostrophic with UG dot del gradients and all that, you're going to get the wrong sign in the Q-vector divergence.
Okay, so you get the wrong sign, but I think the question I was saying is, it's what question are you asking? Are you asking what's the vertical motion look like? Are you asking
Yeah,
a question
I'm trying,
about
and what's the physical process that's giving me the vertical motion field? And I can't use a Q-vector to get it from this. In this case convinced me that in these types of situations, you're going to be misled on it. So what happens with people just start showing Q vectors and saying, oh yeah, here's the divergence of the Q vectors where the vertical motion is. And I'm going, I'm not sure. You're not convincing me just by showing me that field. That's where the vertical motion is.
because you're saying there's another part of the vertical motion field that's
Yeah,
not represented.
and when you have a situation that's going towards an unbalanced state, you will get the wrong sign.
We're in complete agreement that an uncareful, uncritical use of any diagnostic is a foolish endeavor. I completely agree with that.
And
So
that
you can find plenty of environments where you really would be ill-advised to use the quasi-geostrophic system. Completely agree with that. So we don't have as
And
much
I'm also
agreement.
saying that with numerical models now, right, based on primitive equations, not hydrostatic, you're better off using those vertical motion fields and trying to understand what created those vertical motion fields than trying to give me a Q vector analysis off the model fields to say, hey, this is the vertical motion field. No, it's not. The vertical motion field, the models are very good at representing the vertical motion that's related to the primitive equations and the diabatic processes that we feed into it. Very good at doing that. While we're doing diagnostics, I can actually diagnose gravity waves.
My position is just you can separate things better if you know more of the possible approaches. That's all I'm saying. And I think you agree with me.
Yeah, as long as you're willing to admit that by diagnosing it, you actually can see where it doesn't work.
That's exactly why I think it's
And
insightful.
I don't think a lot of people are doing that.
Yeah,
They just take it and they run with it. And effective
That's
diagnostics are even worse. You
I
gotta
agree.
be really careful with those.
I agree. Those
Well,
are
that's
bad.
that's the warm air infection and PBA. People still go back to that, and it's like, wait a minute. I'm giving you primitive equation models, and you're coming back to me with warm air infection. And there's also in the map, I've seen some things with low-level forcing again.
I agree.
Well, this brings up an interesting question on the education process. What should, in a synoptic class these days, or mesoscale class, they really kind of blend together now, a lot because of what you're saying, but how do you teach this class? You know, when, teaching QG is like part of the problem, but there's all these other things that happen in the balance equation. And how do you teach that now? What should be the curriculum?
Okay, so I taught for about a year and a half, and then I ran out of gas. That's one of the reasons I left going to Goddard too, by the way, to do all the research you want. I admire folks that teach. It's really a hard thing to do. And it's even scary in that the students can rate you almost on an instantaneous basis. You get zapped. What's that? There are apps now where people rate teachers, rate restaurants. I mean, it's just unbelievable. You have a bad day and your whole teaching career is shot. So
that's a bad diagnostic.
That's a bad diagnostic, and it's not even effective.
Right.
It's subjective, right? So, but there were a couple of things that when I went to Larry Dunn left the letter, so really, we had much stronger arguments about this than Larry Dunn. I thought one time that he was going to drive off the road with me arguing about this. He's now teaching at Utah. And he asked me if I were teaching a course along the lines, and you started like, what would I teach? So I said, there were 2 pages in Holton and Martin. I'm sorry, in Holton's book that talks about the assumptions made for the quasi-geostrophic view. I said I would make sure that got 1 or 2 lectures, just the importance of those assumptions, because the students would have to understand how far they could take this in terms of whatever insights they believe they're getting from it. Okay? Understand the assumptions. And then I said, and it was more or less along the lines, any approach, what are the pros and cons? There are pros and cons of everything. What annoys me about the quasi-geostrophic is the separation when they do just the vector field and the overuse of it in situations that it shouldn't be used for, even on the mesoscale. That they ought to understand how the assumptions are working against its use.
I agree 100%.
All right? So I found that, at least when it was taught here, those things weren't emphasized. And when I was going to conferences arguing with Hickory or Jackham or Sanders, that they were applying these things without these equations and sets of equations without really fully expanding upon the assumptions. I think that's really important. The other thing is, as the scale compression, I really would go through the slow mode response, the geostrophic, as a load develops versus the impact of isobaric, and then get to the gravity wave mode, because first of all, the time scales change and the response of the winds change, and get an understanding of that. And as you get to the gravity wave aspect, you pull full smaller scale where any kind of quasi-semi-geostrophic is just not applicable.
So it's
and understand that spectrum. So when I show the Snyder case, what is rapid cyclogenesis in that case? Because it occurred when that high amplitude gravity wave passed through the center of the low. So it's not Sutcliffe self-development. The larger part is, all right. But what was going on in the inner core of that site? And I'm willing to bet that happens more times than not when you see these rapid, explosively developing storms over the middle of the ocean. It's really amazing how the hurricane force winds move from the southwest quadrant through the center of the low just to the northeast. There's got to be some gravity wave interaction. So, if you understand how these different things work, you might be able to start teaching how they work together under certain circumstances, and that's when you get the extreme events. So, spectrum of responses. And this one, to conclude that there was no, I'm telling you, that's what drove me to 5 papers. Just tell me there's no upper level force and I'll find it for you.
Well, we talked about that at dinner the other night. That's crazy. That was a really bad argument for the other side to have. We agree on that. That was terrible.
So Lance and I have agreed to meet halfway. So I better appreciated the role of the boundary layer by the time I got done with those papers. And he was always looking for upper level force in there. So when they wrote that stuff, that's what drove me to this.
I can understand that.
So if you're teaching a synaptic meteorology course, would you still teach Q vector, or would you just to show the limitations of it, or would you?
I would try to get folks into the primitive equations more, through the use of the models, but I just wouldn't jump in. There were 2 things. First of all, I really encourage people to start plotting up data and getting insights into what the data is showing you, because Lance still does that, by the way. He will not just go to a convenient analysis scheme. try to get some kind of routine established where people are actually starting to live with the data set as they're going into the case study, so they even understand because there are restrictions on analysis too. Right? And then work the way towards model applications for diagnostic studies. That's point number one. Point number two is Eulerian versus Lagrangian. So this is the thing we talked about the other day. All right, so you got a jet, and you got, let's say you just got a front tube here that supports the jet. And then this goes off. So we all agree that the gradient is less here and less here. And if you have a parcel that's passing through this jet, with respect to that moving parcel, this part is frontalytic in the x-ray. Right? From a Eulerian perspective, at time, you got an indirect circulation here. So this is warming. It's thinking at warming. So you got warm air warming. You got cold air cooling. So from a Eulerian perspective, you got frontogenesis. Most of the frontogenesis work that was done in the 50s, 60s, and even into the 70s and early 80s was all Lagrangian. So you got Mel Shapiro walking around telling you, Uccellini doesn't know what the hell he's talking about with indirect circulations because this area is frontolytic. And it was just a matter of understanding which framework you're in from a Lagrangian versus Eulerian.
It's a matter of adding an adverb. Horizontally frontolytic, vertically frontogenetic.
They didn't make that distinction.
I know. It's
Right.
unfortunate.
Right.
Clear it up.
So the thing is, this is really important because you're actually creating development potential energy here, right? And you're destroying development potential energy here as your jet max here, so you're providing the kinetic energy downstream. So from an energy budget point of view, this is really neat because this is explaining the propagation, the ability of the jet stream to propagate and have a thermal field that's supporting it as it propagates. How you understand that and represent it is a function of whether you're doing Lagrangian or Eulerian. So I did both. As we were working here, Ralph Peterson actually came up with and I came up with a new way of doing trajectories from a computer science course that we took across the street and published a paper on that. So we were doing trajectories in the field and gaining insight from those trajectories. It's really tremendous. And then the back trajectories, the isolated stream flows and things like that. I think that needs to be taught more, that people understand that distinction. There's still a lot to learn in this stuff. I'm sure I have lots of surprises for us. Anyway, what else you want to argue with me about?
No, we're not even arguing. We're not even
I know,
arguing.
you're right. It's true.
And the same
I got to tell Larry.
I got to teach this stuff. It's exactly what I'm doing when I'm important to you. Exactly that.
So you know Larry Dunn, right? Did you know Larry?
I don't know him well. I met him. Yeah.
He actually picked me up from the airport. Yeah. Right? Started arguing with me about some things that we got arguing about this stuff. His wife is home. We put the two kids to bed. We're going to have dinner at their place. He's yelling. By the time we get to the house, he starts yelling and screaming about this stuff. Isn't he our guest? So I said to her, I said, no, this is okay. This is okay. He hasn't gotten to the trigger point yet. Yeah. So anyway, very controversial stuff. What was going on in this school and its emphasis on isotropic. Oh, the other thing is cross sections. Having the horizontal. We used to do cross sections through these jet systems, not just for the sake of doing cross sections, but then to adjust the temperature fields on any individual pressure. So we were actually, by using the cross sections, saying, no, the front really isn't over here on this horizontal map. That front's over here. So we would adjust our analysis. So going back and forth between the cross sections, to really, you can actually start getting sort of the detail like Mel Shapiro shows in his analysis. It's a combination him using cross sections and then actually influencing the heart, and then back. All right, because you never have enough data for the actual soundings unless you're flying airplanes to be able to show that. So that was the other thing.
Well, that's the beauty of soundings. They have very high resolution in
Right.
the vertical.
So how do you map that into
Yeah.
the horizontal
You
map?
can get that in the horizontal from
Right.
the vertical
Right.
cross section.
Yes. And that's what we used to do right in this room. And that's why, so explaining to your class, we used to map the 12Z fields here, well, we're on the 14th floor. The 0Z fields we did in real time would be on that back wall, and then the new ones were the next 12Z. So we kept a time continuous set of cross sections that would influence our horizontal analysis from Synoptic Lab to keep our mindset on what was going on. One thing we didn't do in real time back then was the trajectories. That came with the data.
So with the new types of analyses, simulation systems that are being used with data, do you have, one of the things that we've noticed is that the maps get look noisier than what we saw in the old time fax maps.
Right.
But do you have greater faith in those analyses? Again, you have to look at the raw data themselves, but do you think they're really giving you a better depiction, even though they're noisier, of what the true state of the atmosphere is?
So Paul and I wound up with the 70 cases in the book. We actually used we did a reanalysis. We didn't take the reanalysis from course of resolution. We did a reanalysis at 27 kilometers for the scoped in area, and then allowed the data both before and after the influence. And we were still finding, at least we were getting some representation, but we were finding weaknesses in cases. The actual initial analysis scheme that feeds into models, that I still think there are issues. And the case that I challenged Durbin with, as with the new data assimilation, is the January 2000 surprise snowstorm.
Yeah.
And in that case, we had a field, this southeast U.S., it's supposed to be Florida, and then over here, there was a developing trough here, and from the hand analysis, there were like 20 wind reports from jets, the soundings, whatever, that basically had flow, pretty strong flow like this, cutting across, a very cross height flow, definitely an accelerated flow field. And what that meant to us is that whatever developed would hug the coast as it moved north rather than move out to sea. So the forecasters, the models were all taking it out. What the models did was basically took the wind, rejected these wind fields and provided a wind field that looked like this, basically. More in balance. And we still got those data sets. Jeff Manikin was coming up with an EMC at the time. This is the surprise snowstorm. The week after we got the new computer and made a big deal about getting a new computer, and Oliphant with a cartoon on it that I now have hanging on my wall. So when we introduced the new analysis schemes, it's starting to show more cross height flow, but not to the magnitude that actually existed. And there's a latent heat feedback that's going on at this time into this field, and it's like there's an outflow coming out of this thing. It's like this explosive, like we were showing yesterday with the subtropical jets, which is flowing right into this thing. That unbalanced flow is really unbalanced. The angle to the height field of these winds increased from the 6Z run and the 0Z analysis that we had. So it was actually going more into an unbalanced state during this time. Sure enough, 15 hours later, the low came right up at us, and we got about 18 inches of snow with 30, 40 mile an hour winds. It wasn't predicted. That people woke up to. Not pretty exciting. So anyway, that case, January 2000, the one that Tracton wrote up in the Sanders book. Yeah. That'd be a good one to see. If you're doing analysis stuff, that would be a good case to see what the new analysis schemes are doing.
One of the things I did with working with Darrell Price was we looked at the development of something in the southeast that seemed to be missing from the analysis. There was a small...
For this case?
Yeah, for this case, there was like a pre-existing low rotisserie anomaly that was created diagrammatically. I think Gary Lackman had looked at it from a different perspective and keyed in on something also in the southeast.
Yeah, and it wasn't clear whether that would actually interfere with the development. And sometimes these systems get too close, the fields just don't mesh. But it seemed to be part of driving this trough, and instead of driving it straight out to sea, you started getting self-development.
Yeah,
but it was driven. But it was driven. It was accelerated. The time scale much shorter than you would get from self-development. By the fact that it was diabatically forced and you were getting these vertical displacements. I think that's what was happening here, is that you were getting vertical displacement of parcels from below through the latent heating. And they were popping up perpendicular to the, to these height lines. And the initial analysis was saying, what latent heating, right? Boom. So it just turned the wind field and did that.
And so we saw when we put that additional feature into sort of crude reanalysis of that in the case study that we got a more improved
simulation. So the analysis that I was shown was going in the right direction, but it just didn't give us the magnitude that was actually there. And it wasn't just one radius sun. There were all, like I said, all the flights coming out of Atlanta were showing these wind fields. We had a tremendous number of wind factors around, and you would have thought that the analysis scheme would have held on to it just by the mere fact that you had it, boom, just shifted them right over.
That takes all the kinetic energy generation away from the downstream jet.
Yep.
Yeah.
Disappears.
But this is that vertical displacement, by the way, which is also not accounted for in the Saussure stroke approach, or semi. So that's that kind of relationship that one needs to have insight into as well. Anyway.
That's great.
By the way, it's too bad John Young isn't here, because we used to argue about this as well. John was brought here to teach quasi-geostrophic dynamics at MIT. He was an office mate at Holton when he was at MIT. And so he was here to teach quasi-geostrophic. And I used to argue with him as a student. He did have power to the pen, though. Yeah.
The only power that there is.
That's right. Anyway, what's the weather going to be? I'm not ready to make a forecast.
Yeah, no, we've got Kyle and Zach going to do a review discussion. Thank you, Louis.